Greetings, folks. So in this video, I want to talk about another example, or work through another example. And particularly this one I thought was really interesting because it didn't kind of work out the way that I expected it to. So the problem that we're going to work through today is this one right here on the right side. Tangent of 2 theta is equal to 2 cosine of theta. Sorry, tangent 2 theta plus 2 cosine of theta is equal to 0. So let's go through our steps like we had done in the last video. Step 1, rewrite our equation and get it down to, again, a much simpler equation. We have a couple issues here. One is that there's all tangent and cosine, so we have two different trig functions, so that makes our life difficult. We also have a double angle and then a single angle, 2 theta and theta, so that will also be annoying. On this one, I'm going to pull out the double angle identity for a tangent. This is not the only way to do it. This is the way that I thought of it first. So I'll just share what I did and kind of what led me to like this kind of interesting conclusion or interesting kind of discovery that I had to go through and wrestle with. So our tangent double angle formula is 2 tangent of just theta over 1 minus tangent squared of theta plus 2 cosine of 2 cosine of theta is equal to 0. Okay, so at this point, I want to bust my fraction. Would rather not have that. So let me write down step 1 here because we're doing step 1. So I'll multiply everything by 1 minus tangent squared. Okay, so that will bust this fraction on the left side right there. I do have to distribute that 2 cosine into the 1 minus tangent squared. And of course, the right side is just going to stay 0. So I have 2 tangent plus 2 cosine, and I'm going to, just for sake of making it clear, I'll not distribute it yet, and then I'll distribute it in the next step. So now I'll distribute. Let's see, so I have 2 tangent of theta plus 2 cosine of theta minus 2 cosine theta times tangent squared of theta is equal to 0. It looks like I made a big mess, but and well, I did, but I did clear up some issues. One is that I cleared out the fact that they have different arguments, so I have 1 thetas all over, and we have no more fractions, which is nice. Our other favorite identity, or one of our favorite identities, is to rewrite tangent as sine over cosine. And once I do that, we'll see that I can actually get rid of the denominator signs by multiplying everything by sine. So let me just give myself a little bit more space here. 2 sine over cosine plus 2 cosine of theta minus 2 cosine of theta times sine squared theta over cosine squared theta. Now we can see here that this one of these cosine and one of these will, again, cancel out. So I can just multiply everything by cosine. I don't need to multiply everything by cosine squared times cosine of theta. Okay, so we're left with 2 sine of theta plus 2 cosine squared theta minus 2 sine squared again. That's equal to 0. Almost there. Again, I saw a mixture of sines and cosines, 2 different trig functions, but I can get everything into sines by using our favorite Pythagorean identity. So I'll trade this guy out for a 1 minus sine squared. Fill in everything else. Minus 2 sine squared of theta is equal to 0. Okay, in the interest of time, because this, I already know it's going to be a long video, I'm going to speed this process up, but we can see that we have something squared and plus something, right? X squared plus x plus a constant is going to equal 0. So this is a quadratic. And so I will go for, and it turns out to be a factorial quadratic. So I'm going to go ahead and factor it already. I have 2 sine of theta minus 1, actually it'll be plus 1 here, over sine of theta minus 1 is equal to 0. Okay, a lot of the 2's will end up canceling out. You'll divide everything by, you'll divide the both sides by 2 to get here as well. Okay, at this point, then I can use my 0 product property and get that sine of theta here has to be equal to -1/2 or sine of theta is equal to 1. This one's easy peasy because I only have one angle that does that. Theta is equal to pi over 2. Again, and in every revolution thereafter. So, oops, plus 2 pi n. In the case of negative 1/2, again, just quickly draw your unit circle. Negative 1/2 is going to happen over here, which would be at, let's see, that'd be 1 pi plus another pi over 6. So that's going to be, what can I think right now? 7 pi over 6. Or down here, and either you could go, again, you could go all the way around, or you could just go in the opposite direction. That's the way I like to do it, which will be at negative 1 pi over 6. Okay, so my angles here are going to be, let's see, 7 pi over 6, again, plus 2 pi n. And then I'll just keep it in green so we can remember where everything came from. Negative pi over 6 plus 2 pi n. Okay, I took a break just to gather myself before we talk about these possible extraneous or possibly lost solutions. So we have 3 sets of solutions here: 7 pi over 6, negative pi over 6, and pi over 2. Okay, the way I want to go about this time, because I feel like this equation was especially complicated with how many things we did to it, I want to go through each part one at a time. And I split it up into kind of 3 main pieces here. So our original equation, which is tangent of 2 theta plus 2 cosine theta equals 0, there are already certain values of theta that are not going to be solutions. Our domain is limited by the fact that we're dealing with tangent. Cosine has a domain of all real numbers. You could plug any angle into that without any issues. Once you do a tangent, though, then you do have issues, right? If your angle, the terminal ray, points directly upward or directly downward, then your slope is undefined, and therefore you have no tangent value. So that's going to happen when your angle that you're taking the tangent of, which is 2 theta, not theta, is pi over 2, or 3 pi over 2, or 5 pi over 2. Again, any angle that ends up looking like this, or points straight downward like that. Okay, so that's going to be pi over 2 plus pi n. In other words, theta cannot be pi over 4 plus pi over 2n. Okay, great. Once we've rewritten the equation using the double angle formula, we actually did change the equation a little bit in terms of its allowable, or in terms of its domain. By writing it this way, well, we have 2 possible things to deal with now. One is that tangent of the angle has to be, again, defined. So I'm just looking at this guy right here. And also, well, this guy too. Tangent of an angle is only possible if the angle itself, once again, is not pointing directly upward or downward. So we cannot have theta being pi over 2 or any multiple of pi after that. But at the same time, we've also introduced a fraction here that wasn't already there, of a denominator of 1 minus tangent squared. So we can't allow that to be 0, because again, otherwise your equation, or part of your equation, is undefined. And so we get this. I'll just show briefly how I got to here, but this just gives us, again, tangent squared cannot be equal to 1. So tangent itself cannot be 1 or minus 1. So that's going to give you pi over 4 or negative pi over 4, and every multiple of pi afterward. That's a way to write it, but another way to write this is actually just say pi over 4, just single pi over 4, plus 2 pi, not 2 pi, pi over 2. And the reason I say this is because, again, we can start with pi over 4 or negative pi over 4. But if I use, well, actually, let me do this one in red. If I use positive pi over 4 and I go around 1 pi, I'll end up here. And at 1 pi again, I'll end up back here. If I use the green angle and go from negative pi over 4 plus pi, I'll end up here or back down here. So essentially, every 45-degree increment in each of the quadrants is going to be tackled by this. So The reason I'm pointing this out is because this was already excluded from the original equation. Okay, so these are the exact same domains. The only part that we now added was this piece right here, or the new restriction on the domain comes from that piece. Okay, so when we go about through all of this, we transferred everything into, we busted the fraction by multiplying by 1 minus tangent squared. We converted everything to sines and cosines, and then from here to here, we multiplied by cosine. So again, I'll write that in here, times cosine of theta, again on both sides, to get down to that final equation where our domain is now unrestricted. Okay, we had to remind ourselves though that this step is only okay so long as cosine of the angle is not 0, because that's when you get extraneous solutions, possibly, right? That's when you have to check, is when you either multiply by something that could be 0, so in this case cosine of theta could be 0, or you divide by something that could be 0, or introduce a fraction, which would be basically dividing, right? So again, once I rewrite it as a fraction, I'm now adding in division by a variable. So this is when we have to be careful. Okay, so once we get through all of this stuff, right? This is how we got to our 3 solutions. So theta has to be 7 pi over 6, again, plus 2 pi n, negative 1 pi over 6, plus 2 pi n, or pi over 2, again, plus 2 pi n. So I don't really want to write the 2 pi n every single time, so hopefully it is not proper notation, I don't think. I'm just going to write it that way. But again, we said up top here, like, well, hang on. I thought you couldn't allow the angle to actually be pi over 2. Right. So this is why it helps to check. But if you go back in time and actually check each of the solutions, they do actually work. All 3 of them work. And it comes from the fact that in the original equation, the very, very, very beginning, the angle can be pi over 2, because this restriction is not one of the original ones, not one of these original ones. It was a new one that we introduced when we added this power fraction. And so I guess the summary, or the TLDR of this entire kind of second half of this video is, in this process, we introduced the possibility of extra solutions by manufacturing this fraction, and therefore generating the necessity, so to speak, of having to bust the fraction by multiplying by cosine later. So in that sense, you could think of it as we added, or sorry, I guess maybe we took away a solution and then added it back in. Right? I took away a solution by turning it into a fraction, and therefore adding possible issues by dividing by 0, again, potentially by introducing opportunities to divide by 0. And then by multiplying right here, this step, we quote unquote lost that extraneous solution. So hopefully that video, again, it's hard for me to kind of say a blanket statement of always do this or always do that. But hopefully this video gives you kind of another kind of set of insights as to when you need to be careful of extraneous solutions or potentially losing solutions here. Okay? Always check though, because it never hurts to check. And also just be wary of whenever you write down or whenever you multiply, just take a second and say, like, hang on, once I've done this of multiplying both sides by cosine, I have to double check, is that solution actually a solution to the original equation? Okay? I know that was probably not the clearest way I could set it, but I already kind of sat on this video for a long time. I had a conversation with ChatGPT over the last couple of days, and this is kind of the clearest way I could relay that to you. Okay? But I encourage you to, again, have your own conversations with each other, or if you don't want to make friends, find a useful AI tool that you trust and use it. I think it's a wonderful tool if you use it properly. Again, try the problems on your own before you resort to outside resources. Okay. Thanks for watching. Hopefully, see you later.